Hello friends, welcome to my channel Tech Buzz with Pradeep. I hope you are doing great. Today I am with you with a new topic, variational autoencoder. This is a very important concept in generative AI and it is very important to understand it because this is highly used in the industry nowadays. Okay, then starting with the first slide. Here I have created two images. First, I would like to show you about the traditional autoencoder and the another one is the VAE, Variational Autoencoder design. So traditional autoencoder sampling operations creates a bottleneck because back propagation cannot flow through a random node. Inside into the traditional autoencoder, back propagation doesn't happen. After bottleneck, we have sample processing. Okay, so the problem is that we cannot run back propagation and push the gradient to the sampling nodes. And in order to run our gradient to our entire nodes and to train everything and end to end, we are going to use some trick. This trick is available inside into the variational autoencoder design. So in few slides we will discuss this trick. Before coming to that trick, we will discuss about the difference between these two, the fundamental difference. Unlike traditional autoencoder, which maps the input onto a latent vector, a VAE maps the input data into the parameters of the probability distribution, such as mean and variance of the Gaussian. So here we are getting the fixed length vector. Rather than getting the fixed length vector, here we are achieving the distribution. So here we can see mean vector, standard deviation vector, epsilon. This is the random noise to manage the randomness of G. And this distribution is helpful to do the sampling, and after sampling the data will be sent to the decoder as input. This approach produces a continuous structured latent space which is useful for image generation. Okay, so this is the difference. Here we are having the fixed length vector as an input for the decoder, but here we are getting the distribution, which is continuous structured latent space. Okay. Here in this image we can see the details about the mu, the components. So mu is the mean vector, sigma is the standard deviation vector, epsilon, as we said, like the sigma, epsilon is a random noise to manage the randomness of sample latent vector. So G, which is the sample latent vector, is equal to mu plus sigma epsilon. So mu is the mean vector, sigma is the standard deviation. And this sample latent vector will be sent to the decoder, which is continuous in nature. So this G sample latent vector will understand the distribution of the data here, and that distributions will be sampled here and will be sent back to the decoder as input. This is the way the variational autoencoder works. As I was talking about this, the reparameterization trick. This is the trick I was talking about. So after bottleneck, we have to do the sample processing. The problem that we can't run back propagation and push the gradient to the sampling nodes. And in order to run our gradient to our entire nodes and to train everything end to end, we are going to use the reparameterization technique. So here we will see that G is equal to mu plus sigma epsilon, and this mu and sigma are responsible to enable the model to back propagate gradients in the encoder through by itself, while the randomness inside into the G will be achieved through epsilon. To address the issue of the back propagation, which can't flow through the random node in the traditional autoencoder, we use a reparameterization trick. In our example, we approximate G using the decoder parameters and another parameter epsilon as follows. G is equal to mu plus sigma epsilon, where mu and sigma represents the mean and standard deviation of the Gaussian distribution respectively. The epsilon is the random noise used to maintain a skyticity of G. The latent variable G is now generated by the function of mu, sigma and epsilon, which would enable the model of the back propagate gradient in the encoder through mu and sigma respectively, while maintaining the stochasticity through epsilon. This is the way it works. So mu and sigma will be changing the values. These are the variables which are changing, but epsilon is almost fixed. So this is the trick which is being used for the latent variable generations and to pass into the decoder of the or variational auto encoder. Let us have a quick look of the code in the TensorFlow. Guys, here I would like to say to show you how to create a function for encoding, reparameterization, decoding function. So here is the code of the network architecture, convolutional variational autoencoder. Here we can see three methods: encode, reparameterize, and decode. So X is taken as the input inside the encode, and it is returning mean and variance, and the mean and variance will be fed as an input into the reparameterization, and it will return the G. As we discussed earlier, like G is the mu plus sigma into epsilon. That is what it is returning. And after returning it, it will be fed inside into the decoder. So these are the three important methods has been created over here. So I have shown you very little bit, you guys, so better to go for it into the deep for better understanding. Coming back to the slides now. So logs function in VAE. So here are the two losses in training a variational autoencoder. Mean square error loss to compute the loss between the input image and the reconstructed image. KL divergence to compute the encoded distribution and the normal distribution with zero mean and one variance. So there is a mathematical formula for that, guys, but I have not shown over here because there is a lot of computation formula will be required. So I'm not considering that for now. So we have reached to the end of the session. I hope you liked the session. And if you have liked the session, then please like it, comment on it, and subscribe my channel. Thank you guys. Thanks for joining. Have a great day. Bye.